All right, so in this section, section 3.3, we'll cover the four so-called isomorphism theorems. We call them isomorphism theorems because, they each say a lot of things, but the conclusion for all of them is that some two objects are isomorphic. In the first three, we have an isomorphism between some groups, and in the fourth, or lattice isomorphism, we'll exhibit an isomorphism between two lattices. All right, so let's go ahead and state our first isomorphism theorem. This is theorem 16 that we'll call the first isomorphism theorem. It's often called the fundamental isomorphism theorem because it's really important. All right, so here's how this goes. So suppose that phi from G to H is a group homomorphism, then the kernel of phi is normal in G, and if you look at the quotient group G over the kernel of phi, this is isomorphic to the image phi of G. And I think this was already known, but we will present a relatively self-contained proof. All right, so first let's show that the kernel of phi is normal in G. All right, so let's let G be in G and let Z be an element of that kernel. Then note by the properties of homomorphisms, if we look at phi of the element GZG inverse, we can split that up and get phi of G times phi of Z times the inverse of phi of G. And so remember that Z is in the kernel of phi, so that phi of Z is 1, and so this breaks down to phi of G times 1 times phi of G inverse, and so this is just the product of phi of G and its inverse, which is 1. And so what we've shown here is that GZG inverse is in the kernel of phi, so what it means is that if you take any element of the kernel of phi and conjugate by an arbitrary element of G, you land back in the kernel of phi, and so that was one of our equivalent conditions for a subgroup to be normal, so it means that the kernel of phi is normal in G. In particular, the quotient G over the kernel of phi, the collection of left cosets of that kernel in G under coset multiplication, is a group. All right, and so now we're going to exhibit an isomorphism from this quotient group to the image. All right, so let's write K equals the kernel of phi, and we're going to define a map, say, theta from G over K to phi of G by theta takes an arbitrary coset represented by little g, so gk, and it just applies that map that we're given, phi, to a coset representative. Okay, and so this is defined for all g and g, and so we're hoping to show that this element, this map theta, is an isomorphism. And so the first thing you should be thinking to yourself here is, okay, what we've done is we've defined a map on a set on the set of cosets, but that map is defined not in terms of the cosets itself, but that map is defined in terms of a representative of a coset. All right, so what we need to do is first make sure that this map is well defined, right? If you have two different if you have the same coset, that coset might have lots of different representatives, and so the question is, all right, if you apply this map phi to a different representative, do you still get the same value? Okay, and I think we've been through this argument before, but yes, you do. All right, and so what we'll do is we'll show that that map theta is well defined. All right, so since theta depends on a representative in each coset in G over K, let's suppose that we have the same coset represented by, say, two different elements, G and H. So GK is equal to HK for some GH in G. And now the key is that K is the kernel of phi. All right, well, remember what it means. It means that, in particular, the element little g is in the coset hk, so g is equal to h times little k for some little k in that kernel. And so if you look at theta of the coset gk, this is phi of little g, which is phi of hk. Use the fact that phi is a homomorphism. This is phi of h times phi of k. Use the fact that k is in the kernel of phi to get that this is equal to phi of h times 1, which is phi of h, which is the value of theta applied to the coset hk. And so we've shown that if you have two cosets, gk equals hk, then the value of theta of those cosets is the same, and so theta is a well-defined map. All right, so now let's show that theta is a group homomorphism. So for any two cosets, if you look at the value of theta of gk times hk, remember how our coset multiplication works. You just multiply the representatives and take as that product the coset which contains the product of the representatives. So we're applying theta to the coset gh times k. By definition of theta, this is phi of gh, which is phi of g times phi of gh, which again, by definition of theta, is theta of gk times theta of gh, so that theta is a group homomorphism. All right, so we've established that theta is a well-defined group homomorphism, and so we're trying to conclude that theta is an isomorphism, so the remaining thing is to show that theta is a bijection. All right, so let's show that theta is a bijection, and suppose we have two cosets, gk and hk, such that theta of gk is equal to theta of hk. In particular, that means that phi of g is equal to phi of h. And now, phi may not be injective, so this does not imply that g is equal to h, but we're trying to show that those cosets, gk and hk, are equal. All right? But if phi of g is equal to phi of h, in particular, all right, using our properties of homomorphisms, we have that phi of gh inverse is equal to 1, and thus gh inverse is in the kernel of phi, which is k. Okay. And so remember, we had a proposition that said two cosets are equal if and only if one of them times the inverse, a representative of one of them times the inverse of a representative for the other one is in that subgroup. All right, so by proposition 4, since gh inverse is in k, it follows that the two cosets gk and hk are equal, so that theta is injective. And finally, it follows pretty much directly from the definition of theta that theta is surjective, right? So if you're given an h in the codomain of theta, right? The codomain of theta is the image of g under phi. Then what does it mean? It means that h is equal to phi of g for some little g in h, and thus if I apply theta to the coset gk, which contains little g, I get phi of g, which is h. All right, so that theta is surjective, which completes the proof of the first isomorphism theorem. All right, now we present a quick corollary, and I think we may have already known some of this, but here's a relatively self-contained proof. All right, so let's let phi from g to h be a group homomorphism. Then phi is injective if and only if its kernel is 1, and also the index of the kernel of phi in g is equal to the order of the image. All right, so let's prove. First, let's prove the first direction, or the forward direction of part 1. So let's suppose that phi is injective, and suppose that z is in the kernel of phi. All right, well, what does it mean? It means that phi of z is equal to 1. On the other hand, since phi is a group homomorphism, we also know that phi of 1 is equal to 1, right? Where the 1 on this right-hand side here is the identity in g, and this is the identity in h. All right? And then as phi is injective, well, we have phi of z is equal to phi of 1, but we've assumed phi is injective, and so it means that z is equal to 1. So what we've just shown is that, all right, if you have an element of the kernel, then that element is 1, okay? So which implies that since the kernel is a subgroup of g, that the kernel is just the trivial subgroup containing only 1. All right, go the other direction. Let's suppose that the kernel of phi is equal to 1, and suppose that g and h are in g with the property that phi of g is equal to phi of h. To show that phi is injective, we need to show that g is equal to h. Okay, well, then it follows that, again, using properties of homomorphisms, that phi of the element gh inverse is equal to 1, and so what it means is that gh inverse is in kernel of phi. But we've assumed that there's only one element in the kernel of phi, and so gh inverse is equal to that one element in the kernel of phi, which is the trivial element, the identity. And that yields that g is equal to h. And so we've just shown that phi is injective, completing the proof of part 1. Now, the proof of 2 just follows directly from the first isomorphism theorem, right? The index of the kernel of phi in G is the order of the group G over the kernel of phi. And in our first isomorphism theorem, we've shown that G over the kernel of phi is isomorphic to phi of G, so those groups have the same order. All right, and so let's take a look at an example of how this can be used. All right, let's show that R cross over the group generated by -1 is isomorphic to R plus, where R cross is the group of real numbers under multiplication. All right, sorry, non-zero real numbers. Sorry, R cross is the group of non-zero real numbers under multiplication, and R plus is the group of positive real numbers under multiplication. Okay, and so by our first homomorphism, if we want to show that this quotient group is isomorphic to this R plus, all right, one way we could go about that is to try to find a surjective group homomorphism from R cross to R plus whose kernel is plus or minus 1, right? Because if you have such a homomorphism, then R cross mod the kernel of that homomorphism is isomorphic to the image, but if the map is surjective, then the image is all of R plus. All right, so let's see if we can come up with a map. So define a map phi from R cross to R plus be defined by phi of x is equal to x squared. There are several maps that will work. All right, if you define phi of x equals x squared, you can show that phi is a surjective group homomorphism with that desired kernel. Straightforward exercise there. All right, and so by our first isomorphism theorem, we have that R cross over plus or minus 1, what is that? That's the group R cross over the kernel K, is isomorphic to the image phi of R cross, which is all of R plus. And in particular, R cross over plus or minus 1 is isomorphic to R plus as desired.